Okay, so now we're finally on VSEPR theory. We can look through all of this. So CH3F again determined. So you don't really have to draw the Lewis structure here. You can kind of guesstimate as to what this is going to look like. If in doubt, you would draw the Lewis structure, I suppose. Here you have, you know, would it be better to yeah, you know what? Why not? Let's just do the Lewis structure. C H O F H3. It doesn't really matter where you put the H realistically. 4 plus 3, 7 plus 7, 14. So we have 8, 9, 10, 11, 12, 13, 14. This is our compound. We know it's AX4, so tetrahedral. This will be polar because it has different substituents on it. So this has basically no dipole between the C and H, but there will be a net dipole between C and F, and therefore it's a polar molecule. CH2O. That's interesting. Again, you would do possibly 4 plus 6 plus 2, 6 plus 6 is 12. So C H H O. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is an interesting case because here I kind of do have to look at my carbon atom and realize that there's not 8 electrons on my carbon atom, so I kind of have to modify that a little bit by adding a double bond by removing one of the lone pairs from the oxygen. So now carbon has 8, oxygen has 8, hydrogen have 2 each. This is my formaldehyde or my HCHO. This is a polar molecule. And what is the VSEPR shape? Central atom is carbon, 3 bonds, AX3, trigonal planar. Right? But it is polar. Gallium iodide. Never seen that. I haven't seen that one in a while. I honestly would have thought that was ionic, but I guess not. Well, I believe gallium is under phosphorus. So why would it be an ionic? Oh wait, is gallium under phosphorus or aluminum? It is under aluminum. Why is it not? Interesting. I'm gonna see if I can find electronegativity properties. Electronegativity. Look at there. 2.66, 1.81. What's the difference there? 0.8? Yeah. Oh, I guess it is polar covalent, not ionic. Fascinating. Would never guess that. Okay. Whoops, wrong one. There we go. Okay, gallium. I. Let's see, that's 3 valence electrons plus 3 times 7, 21, 24, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Gallium does not have 8, but I don't think you can do anything about that realistically. Because iodine all have formal chart. Interesting. I don't know if gallium needs 8. I feel like it's one of those weird ones which are okay without 8. Because if I did make the iodine double bond, I don't even think that's possible. I think this is going to be our structure. Although I do have to kind of double check that. But this would be a nonpolar trigonal planar structure, AX3. And whether or not there's a double bond is not really going to change that answer. It's a trigonal planar AX3 nonpolar. CCl2, CF2. So C, Cl, Cl, F, F. This is a tetrahedral molecule. It will have a dipole because not all the substituents are the same. And that's it, basically. NF3 or NCl3. Mm, 5 plus 7 times 26, so N, F, F, F. 26, right? So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. This will be polar because it's AX3E. That is a trigonal planar, so it will be polar. I'm guessing NCl3 is going to be the same thing, but NF3 would be more polar because the NF bond is more polar than NCl3. ICl4 minus or TeCl4. Let's see. Where is tellurium again? It's under sulfur, so that's 6. 6 plus 28 is 34. Eight, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. This will be seesaw shape, AX4E. It will be polar. ICl4 minus would be 35, 36. So here it would have 2 lone pairs. So we'll see. I guess you could. Whoops. No, stop. What was I looking for? I don't even know. Okay, there we go. Sorry, it's hard to say which one's more polar. I'd probably say the ICl4 just due to the negative charge on it. However, there's an interesting case here that we do have to cover. The case of xenon fluoride. So we'll, and this is important to do. The case of xenon fluoride. So now I know I said that all things with lone pairs are automatically polar. I was actually incorrect. Xenon X4 has a square planar shape. And that's the interesting case where the lone pairs actually are able to cancel each other out. The dipole from the lone pairs. And so the F4s also cancel out. So this is a symmetrical molecule. And therefore this will be non-polar xenon F4. If anybody's hearing this now, I will talk about it again in class. That was my bad. I did not account for that when I made my rules. Again, the rules are more of that was an easy shortcut that I just made up to help you. Basically, you have to look for whether the molecule is symmetrical or not. The lone pair kind of destroys the symmetry most of the time, except in this case where you have a kind of lone pairs canceling out. It's not often that this happens due to the shape. Because even like molecules like water, where you have 2 lone pairs and 2 bonds, it's a polar molecule because your lone pairs are oriented in such a way. It's just that this one, the square planar shape, has it where the lone pairs can cancel each other out. So we'll talk about that on Monday. But yeah, just to point that out. Okay. So this is some more polar non-polar questions. We're going to run through this. 5 plus 3 is 8. That means this has a lone pair. The Lewis structure is AX3E, trigonal pyramidal, and therefore it will be polar. CH3CN, CH3C triple bond N. That would be polar just because there's a CN bond. Yeah, I don't think there's really anything you can do about that. Polar. Lewis structure for that will be interesting. We can try that. The Lewis structure for this looks like AS, H, 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 double pair. Sorry, my stylus is behaving weird. I don't really know why. I think if I close the app, but I'm too lazy to do that, so we're just going to continue. Pairs are going to look like lone lines, whatever. That CH3 CN, was it? How many electrons is that? 4, 8, 13, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still need many bonds to carbon, so I'm going to put 11, 12, 13, 14, 15, 16, like so, just so that all my carbons have 8 electrons. You can automatically do the triple bond. You don't really have to calculate formal charges or anything. But here you see that you do have a polar, because this carbon especially is connected to a nitrogen on this side and a carbon on that side, so that's a polar carbon. It will have this is a polar molecule. Cl2O, that's 14 plus 6, 20 electrons. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This looks like it works. This is a bent structure, AX2E2, or angular, and so it will be polar because of its shape, right? This shape actually looks like, and the lone pairs around the chlorine, but this is a bent angular, so it will be polar, even though the substituents are the same. All polar molecules must have polar bonds. Yes, that is kind of a requirement. If you only have nonpolar bonds, it's impossible for the molecule to be polar. And all nonpolar molecules must have nonpolar bonds. That is not true, because even with polar bonds, the molecule can be nonpolar, as evidenced by the case where you have symmetry, same substituents, and no lone pairs most of the times, right? So this part is true, first part, and the second part is false. What similarities and what differences would you expect in the molecular shape of CH4 and CH3OH? Molecular shape, I would expect some differences, because the CH3, if you look at that oxygen right there, the CH3OH looks kind of like this, with 2 lone pairs on the oxygen. So it's kind of bent around this oxygen, so the oxygen looks like that, so to speak. And this kind of looks like a tetrahedral structure. So somewhat like that is what the molecule is going to end up looking like. CH4 is just a plain tetrahedral. So, excuse me. CH4 is nonpolar. It's made up of nonpolar bonds. Part B, its structure is symmetrical, tetrahedral, so that make it nonpolar. This will be a polar molecule because you have this carbon-oxygen bond and the oxygen-hydrogen bond, which make it very nonpolar. Let's do, I think we're going to skip 4 because it's too long to read. I don't even know what that... Yeah, don't worry about that. SF2, molecular shape and polarity. Let's do... SF2 is 6 plus 14 is 20, so sulfur, fluorine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Sulfur has 8, fluorine have 8. I don't need to, all of them have formal charges of 0, so I don't need to worry about that. This will be AX2E2, and therefore it would be angular, just like water. And it will be polar because angulars have 2 lone pairs, and therefore it's polar. PCl4 plus. Okay, 5 plus 28 minus 1 is 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. No lone pairs on the phosphorus. This is a AX4 molecule, so tetrahedral. It will be non-polar because of its no lone pairs and symmetrical structure plus same substituents. So those are the answers to those questions. Again, hopefully we're good with all of this. Okay, where are the questions here? Skip. Oh, here we go. Okay. So the intermolecular forces in HBr are going to be covalent because the HBr bond is covalent. Is it though? It actually might be an ionic bond. Here's where you actually have to look at electronegativity values. I'm not even sure. 2.2 minus 2.9, that's a difference of 0.76, so that's definitely polar covalent, not... Alright, what is this? What do you want? Go away. So that's polar covalent, we know that. Therefore, the intermolecular force is covalent. Sorry, intramolecular forces are covalent. Intermolecular forces will be dipole-dipole forces, because intermolecular forces mean the forces in between two molecules. Intra means inside HBr. So hydrogen peroxide has a higher boiling point than water. Why? Because water looks like this. Hydrogen peroxide, H2O2, looks like that. And if we look at this molecule, both of them have covalent bonding in between their atoms. Water is a polar molecule, has hydrogen bonding. Hydrogen peroxide is also polar on these two bonds. It also has hydrogen bonding, but hydrogen peroxide, I believe, has two... per molecule, it has two oxygens and two hydrogens that can bond to other oxygens and hydrogens. I even suspect there will be some kind of dimerization. You don't need to know what that is, so we're not going to look at this question really. But because you can just say that because there's more possibilities for hydrogen bonding, because there's more oxygen atoms, therefore it has a higher boiling point, I would say. Okay, classify the following compounds. Here we go. Here we have P4. Interesting. P4. I would say that would be a covalent. Well, not a covalent. Is it a covalent network? That's a good question. I'd probably say molecular, non-polar. I'm just going to double check that actually. Type of bonding in P4. Looks like it is. Yeah, it is molecular nonpolar. Interesting. Okay. Na3PO4 is ionic. It's formed between Na plus ions and PO4 3 minus ions. Osmium, just based on the look of it, I'm assuming this is a metal, even though I don't really know where it is on the periodic table. Let's check. Yep, it's smack in the middle of D block, transition metal. metallic bonds, definitely. This is a network covalent solid, silicon dioxide. NH4 plus Cl minus, this is a ionic compound. In between NH4, there's covalent bonds that are formed. Nonpolar covalent bonds, I'd say. Yeah. Soluble in water, has a melting point of 140. We didn't talk about tests. I'm going to do that question. PF2Cl. Just based on the different substituents groups, you probably guessed that it is polar, even if its molecular shape is, which I highly doubt there will be a lone pair on phosphorus, most likely. But 5 plus 21 is 26. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So there is a lone pair on phosphorus. This will definitely be a polar molecule. Germanium hydride, I think that one's called GE. Yep, it's below carbon. So germanium hydride would probably look tetrahedral, and therefore it would be nonpolar because of its shape. We didn't do that. We didn't do that. We didn't do that. We can let that go. That's basically it. I don't know if I should go over all these ones. These just seems like a lot of work. You should be able to do all this based on what we've talked about, so we're going to stop here. I will do a homework video and an assignment video just so that you can review those for tomorrow. Hopefully you're handing in your assignment. I know I said I'd publish this on Friday, but again, I very deeply apologize. Well, I'd like to say I had something important to do, but to be honest, I just procrastinated very late. But hopefully, even if this is not particularly useful for the test, I'll make the test easy. When you're reviewing for the exam, you can just go over these videos and it will be useful to you then. Yeah. So I guess I will see everybody in class. Peace.